Hello and welcome to another Würth Elektronik eiSos webinar. My name is Eleni Stark and I'm gonna moderate this webinar today. We are very happy that we have so many participants today who took the time to participate in our webinar. The topic of today's webinar is use of MagI Power Modules as flexibly adjustable constant current sources for a variety of applications. Our speaker today is our product manager Roland Kratz. He will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You'll be muted during this webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via our chat function. You'll find the chat function in the webinar control panel. The webinar will be about 20 to 25 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 minutes in addition scheduled for this. If we are unable to answer all your questions within these 10 minutes, we will answer all of the questions after the webinar via email. If you still have other questions after the webinar, please email us at eisos-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you fill out the survey and help us to improve our webinars. The link to the recording of today's webinar, as well as the presentation of the webinar, will be sent to you a few days later in a separate email. You can also watch the recording of today's webinar a few days later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. Now I will hand over to our speaker Roland Kratz and I wish you an exciting webinar.
Welcome to the webinar of Würth Elektronik eiSos. My name is Roland Kratz. Today I would like to show how to turn a MagI Power Module that regulates to a constant output voltage into regulating to a constant output current. This webinar is based on the reference design MagI Current Source, which will be explained in detail within the next approximate 25 minutes. With this webinar, we want to motivate every design engineer who needs a current source to realize this with a power module. The advantage of this is that there are many switching regulator modules available on the market that make it very easy for the design engineer to realize a voltage regulation. Current sources, as easy to use and small modules, are in contrast rare to find and usually have only smaller currents to offer. For this webinar, it is of an advantage to know the basic function of an operational amplifier. However, without this knowledge, you will certainly have fun with a later test of the circuit. The points of the agenda. We take a look at the features of the MagI Current Source. We show why in LED driving and when charging batteries and supercaps, a current source is the best choice. The function of the MagI Current Source, simply explained with a functional diagram. A detailed insight into the schematic. Practical compensation of current regulation without poles and zeros and without mathematics. And we show two other reference designs as an overview, which are also intended to work as a current source, each with variations in circuit design and functionality. Here we see the MagI Current Source with our LGA16 3A power module. Instead of this LGA16 module, any other MagI Power Module can be used as a current source if it has an accessible feedback pin to set the duty cycle and thus the output voltage by an external regulation loop. On the left, we see the input voltage. On the right side, we can draw the output current up to 3 amps, and we zoom into this board. We see on the left the adjustable current limit and also the end of charge voltage. Here you see various voltages which are common with nickel metal hydride batteries, lithium ion batteries, And here you can adjust the current limit starting from 350 milliamps up to 3 amps. We also have an external current limit where you can apply a DC voltage from 0 to 3.3 volt or a PWM voltage also. Which current limit you want to use, external or internal, you can choose here with the appropriate jumpers. Current regulation is needed to maintain the operation point of an LED. Due to the normal operation in the area of the steep slope of the LED characteristic curve, current regulation prevents the LED current from exceeding its maximum value. Although, with a series resistor added to the LED, the current change caused by temperature change can be compensated, but this results by using lighting LEDs in a very high power loss, which are no longer state-of-the-art. Of course, you can also charge batteries and supercaps with the current source. Due to the regulated current, you can operate these and, of course, LEDs safely within their operating conditions. Not to forget, if the load changes, the current remains constant. A typical power module regulates to the output voltage, not the current. If a power module with a regulated output voltage is used, the current is only limited by the internal overcurrent protection. If such a power module is used, for example, to charge supercaps, they act as a short circuit to the power module. In this case, the current is limited only by the internal overcurrent protection of the power module. This can be seen in the datasheet of the respective power module. With the LGA 16 3 amps power module, a maximum of 6 amps is possible, highlighted here. How the overcurrent protection of the power module works can be found in its datasheet. On the right, there is a picture taken from the datasheet which shows when the current limit is reached that with each new switching cycle, the on time of the high side MOSFET is aborted when reaching the overcurrent protection limit, resulting in a smaller duty cycle and consequently results in a reduced output voltage. Now we look at the functional diagram. The maximum output voltage is defined by the resistor divider R1 and R2. This is the voltage limit set by the jumper when no load is applied. It is also the end of charge voltage. The output current is measured by the shunt resistor RS. The error amplifier prevents the output current from exceeding its set value by lowering the output voltage. When the load resistance drops, the error amplifier reduces the output voltage to maintain the current limit. We take a look into the schematic. We have here the input and the output. You see also the appropriate pictures to the highlighted areas. Here we have the input-output bulk capacitors and connectors, the input filter, the output voltage resistor divider, which is equal to the resistor divider if you use a power module only in voltage regulation mode. We see the internal current set value. This means here we set the output current limit. It's just a resistor divider from the supply voltage of 3.3 volt divided down to as a set value for the regulation circuit. The auxiliary supply of 3.3 volt supplies the operational amplifier, and on the right side is used as a reference for supplying the set value. Here in this schematic, an operational amplifier is used, which has two amplifiers inside in a package. So we disable the second amplifier that this amplifier does not disturb the operation of the other amplifier. it's important to connect the plus input to low impedant point like ground or Vin, or for example 1 volt from somewhere where it's available. But on ground, it's connect this to ground is a common thing. Also, we have an external input of the set value where you can apply a DC voltage or a PWM. In this example, we set the output voltage or the end of charge voltage to 14.4 volts. Now we want to set the maximum output voltage. This power module is in constant output voltage regulation mode, like normal buck regulator you all know. The diode on the schematic blocks any current injection while the external regulation, because the external regulation is not active. The feedback is always regulated to 0.8 volt, which is also the internal reference of the power module. We define with the 590 ohms resistor the 1.36 milliamps, which all the time flow through all resistors. So it's the normal voltage regulation. No interaction with the feedback. When we want to limit the output current, we want to interact with the feedback. So here the output current reaches the set limit. This means the external error amplifier controls the output voltage of the power module. In this case, we will show that with the interaction directly at the feedback, we can change the output voltage. In this example, 360 microamps are injected from the error amplifier into the feedback node. And here again, the power module regulates the feedback voltage to 0.8 volt. This means that the output voltage must drop down, that only 1 milliamp are now flown through the resistor, the upper resistor of the resistor feedback divider. In the feedback node, we see the 1 milliamps and the 360 microamps, which in sum is the 1.36 milliamps. So while increasing the current injected into the feedback node, we let the output voltage drop further. By the way, if you rotate the diode 180 degrees, with an auto regulation, you can increase the output voltage. But in our application, we only want to decrease the output voltage. In the schematic, there is a regulator, and on the right side, you see the schematic of this regulator you found in the schematic. This regulator is of PI type. It has a proportional value and an integral value. C1 is used as a high-frequency shortcut. I always place 2.2 pico in this circuit. R1 and R2 creates the proportional value. C2 and R2 creates the integral value. C1 is highlighted too because, yes, it participates in the integral value, but normally C1 is very, very small compared to C2, so we can neglect C1. C4 decouples any set value circuitry from affecting the P and I values. This is quite important because when you generate a set value, which means you tell the system how much current you want to allow, then you can do it, for example, with a potentiometer. This means you have a reference, and this potentiometer creates the voltage between 0 and 150 milliohms. 150 millivolts. And this resistor changes while rotating the potentiometer. This means this changing resistor is added to the resistor R2. And if you look into the formulas for the Kp and Ki, you will see that you instantly, when you rotate the potentiometer, you change the parameters for the regulation, for the compensation. And this is not what we want. C3 and R3 are used as a protection of the non-inverting input of the amplifier. The drawback when you use this is it will delay the actual value of the current. The diode D1 only conducts and reduces the output current if its actual value is equal to the set value. The feedback pin is always 0.8 volt constant because it's regulated by the power module itself. The output voltage of the error amplifier is nearly constant. Small change during load transient. And the current regulation must be much slower than the internal regulation of the power module itself to prevent critical self-excitations. As a result from this, we can set Kp to 0. This means the resistor R1 is 0 ohm. Now we have C1 and C2 directly parallel. So we can remove C1 because C2 acts now as a high frequency bypass also and creates the integral part. When we clean up the schematic and don't draw the components we do not need, we get this schematic on the right side. Only an integrator is left because for turning a power module voltage regulation into a current regulation, we can handle this only with an integrator. And because of the regulation speed of the error amplifier must be slower than the regulation of the power module itself, it's a good thing to start C2 as an 1 nanofarad capacitor. If you try to find the right integral value, you can use as R2 an 100K potentiometer. Best is a non-inductive potentiometer, and rotate it to the point where you have a really fast regulation, like seen in the graph, and you won't have any oscillation like you see in the graph now. The ringing you see comes from the delay of the actual value. This means the pulse current through the LED is also flown through the resistor RS with a 50 milliohms. And this information of the actual current is delayed by R3 and C3. The test here is performed with a functional generator applied to the ground pin and to the PWM 3.3 volt pin and set to 200 Hertz. And it results in a low current of 400 milliamps and a high current of 1.7 amps. This graph is the output current, and it's measured with a current probe. Now, it looks the transient response, the green graph, looks not so good because you have oscillation after the rising edge and after the falling edge because of the delay of the actual value. Now we have two options. We can make the regulation speed of the error amplifier slower. This means if you exchange the 1 nano C2 to a 2 nano 2 or a 4 nano 7 capacitor, you will see that the oscillations on both edges will disappear. With 4 nano 7, you won't see them anymore. But the regulation is quite fast, and if we want to keep the speed of the error amplifier of the regulation, we have another option to remove C3. R3 and C3 are in this schematic because if you have an output capacitor on the reference design or an additional output capacitor, and you have an open circuit, you will have the maximum adjusted voltage, for example, the 14.4 volts. The capacitor is charged. If you do a short circuit, then you immediately have a high inrush current into the 50 milliohms, which may generate a voltage maybe up to 10 volts for a very short time. And the error amplifier is supplied with 3.3 volt. This means at the non-inverting input, the voltage will be too high. The error amplifier gets broken. And this is a really common topic when current regulation is designed. That in the first step, it looks good, but when someone performs a short circuit, the error amplifier gets broken. So if we remove the capacitor C3 and do not delay the signal anymore, the graph looks like this. And this looks quite good. This is the most easy solution to perform current regulation. So here also 1 nano as starting value. You can change it if you want. If you make the 1 nano smaller or higher, it will result directly in the transient response, the green graph. If you replace the 1 nano by a 470 pico, for example, you will see sharper edges after the rising edge and after the falling edge. If you decrease the capacitance value further, you will end up in starting oscillations like we saw on the last sheet. If you increase the 1 nano value, then the edges, which are a little bit round, starts to get rounder and the rise time gets slower. So we have similar reference designs which do basically the same, but with variations and functions. We have the reference design 178001. It's also a current regulation. It's intended to be a LED driver up to 1.5 amps. And the design is made as a PCB which directly allows pick and place. Also, we have another reference design, the 178002. It's a QFN 41 packaged power module with maximum 50 volt input. Here it is used to create a laboratory power supply, which you all know from your lab desk. You see the two potentiometers for voltage adjusting and current adjusting. And in between the both potentiometers, we see an output on-off switch, which interacts directly at the enable pin. On this board, we have two different regulation loops which interact with the feedback. These reference designs you will find on our homepage under the electronic and electromechanical components and the product catalog. On the right side, you see the reference designs. And if you click there, you also will see the design notes for these reference designs. Also, we have more application notes. You will find also under electronic and electromechanical components, under electronic application notes. You see on top a lot of DC-DC converter application notes, and below many other topics. So many thanks for your attention. If you want to get in touch with the Power Modules team, then please contact this email address.
Thank you very much, Roland, for this great webinar. Now we would like to turn our attention to your questions, and we will just wait a little while until some questions have come in. In the meantime, I would also like to draw your attention once again to the fact that in a few days you will also be able to view the webinar once again on our website, and also we will send you in a separate email all the documents like the presentation and also the link to see the webinar again. So now we will check your questions. The first question: can I parallel those boards to have more current?
Yes, basically this is possible. There are some things to consider, as on these boards we have a switching regulator. If you parallel switching regulators in constant current mode, it works quite good if the regulation loops of each board is slow enough. If not, it can lead to oscillations in between all output voltage lines. Which means if one output is, for example, 10 millivolts higher than the other paralleled output, then you have some resistance in between, also maybe some milliohms, which leads to currents flow from the higher output voltage through the one which has a lower output voltage. This has to be considered, and if you see oscillations, you can damp these oscillations in the output lines by a series resistance, a low series resistance, in series with the output cap. But I think the first thing, if a slower regulation speed is okay, it's the best to do this first.
Thank you very much, Roland. Is it possible that one of the new power modules can be used directly to charge LE-POS, or do I still need a charge controller?
Yeah, basically you can use any power module. This is an order code, which is quite new module, but this behavior is exactly the same like other power modules we have. You can directly use these power modules to charge any accumulator or battery which is available. One thing to consider is to look at the best at the specifications of the batteries, which maximum current, or if you want to have a trigger charge, for example, or some special waveforms for charging, everything is possible with this reference design, or with in general with a power module controlled by an external error amplifier. Because as we saw in the graphs, if we saw the transient response, I used the signal generator and adjusted rectangle waveform. But in general, you can use an arbitrary waveform of your choice. So as far as I need, you don't need an extra charge controller, because everything what you can you have everything what you need to charge accumulators. The functions which are not implemented if you use a power module with a current regulation is, for example, monitoring the temperature of the batteries.
So there's also another question. It's why a PI regulator and not only a P regulator?
Because a P regulator is not necessary in this case, because a P part, you really need a PI regulator if you compensate buck regulator itself. But then you have a really fast regulation. And if you only use a P regulator, you will not end up in exactly the current you want to have. You need an integral part if you want to have the actual current exactly like the set current, the set value of the current. I think maybe there's a mismatch in the question.
So maybe the person can just write us an email to the announced email address powermodules@we-online.com, and then you can also specify your question and we can get deeper into it. We just got one last question and then we're already done. It's can I replace the LED with an inductor to demagnetize tapes?
Yes, basically you can have any load you want. An inductor delays also the actual current. So if you look at this graph, we have a transient response, the green graph. If you insert an inductor, you will also delay this graph, because if you have an inductor inside the transfer path of the regulation, it will delay the actual value, which means you will delay everything. But this is possible, and to supply an inductor. But basically, I think it's the best idea to demagnetize tapes with a sine wave, which is possible here because a sine wave needs not high. You can amplify a high speed with a you can inject as a set value a sine wave, and even if the integrator is quite slow, you will have as an output current also a sine wave. So this will work if you use a sine wave.
Thanks once again, Roland. For now, I don't see any more questions. We're going to end up the webinar here right now. Thank you very much once again to everyone who joined us today. We will be happy if you just check our next webinar dates on our website and also participate in one of our next webinars again. Thank you very much once again to our speaker, Roland Kratz, and have a nice day. Bye-bye.